So welcome back, everyone. So hopefully everyone has had a chance to turn the first homework. So if not, so let me make sure YouTube is all working. Okay. So if you not have a chance to turn the first homework, just a reminder in the late policy, you can turn it in up to, if you turn it up to 24 hours late, you only lose 10%. So I would, if you haven't turned it in yet, I'd recommend you still doing that. You can turn in up to 48 hours late, only lose 20% as well. Also you will get to drop the lowest score in the homework. This will be tabulated automatically inside Canvas. So when you see your grade in there, it'll automatically be dropping the low score. If you're just taking probability now and this is hard for you, that might be okay at this point. But I would not recommend planning on dropping the first one. You might want to save that in your back pocket. And as is the university policy in this semester, if there are some medical things which are coming up, which happen, please just let me know, and so I can be accommodating. So let's look at the schedule. So you turned in the first homework today. The second homework is not due for the homeworks are due, I think, every 3 weeks. Okay. The next homework is posted. We posted the second homework already. It'll have to do with the next 2 sections of class. And may have to a little bit to do with or starting this section, which we're going to cover today. So you'll be able to answer those questions having to do with this section, and then it's going to get into a little bit of the background in linear algebra. You'll get to do some very simple things, and you're allowed to use Python on this to do the calculations. I'd recommend you do it in Python because we'll be doing everything else in Python, and so we'll again do some collab notebooks in class to kind of see how to do that, and again how it's quite easy. Should be quite easy to do all the things I'm going to ask you to do. So that homework's out. You could start working on it, if you want to, but some of it we haven't covered that material yet. So the quiz 1 also took place on some Monday after class. I'll say just a couple things about that. I'm not able to post the solutions yet. I had to delay that for some reasons, but those should be, should be able to see the answers if you're unsure about them so hopefully tonight after midnight. Hopefully those will be finished grading by the end of the week. So I had thought maybe this quiz would take on average 10 to 15 minutes. The average time was much longer than I anticipated. So far the grades look fine on the parts that have been graded, but we'll see how that goes. The average was closer to 25 minutes out of 30, which is not what I anticipated. So as part of this, with the we'll try and continue to kind of adjust these things, and I hope that the next quiz will again be closer to the 15-minute average amount of time. I spent a lot of time trying to format the text time. So I was, I guess, maybe overly encouraged by how long I asked the question on quiz 0 about how long it takes you to write this expression. And the average time was about, so it was only about 2 minutes for that. And I figured this one was not that much more difficult to format than the one I gave you. But I could see how it's possibly it would be. So, I'll try and account for this as well. So I think this quiz is worth like 3 or 4% your grade, so don't sweat it too much. If you think you understand, then that's great. Even if you have trouble formatting, we'll try and account for this in the grading and be flexible about that. Yeah, so yeah, I'd intended with quiz 0 to kind of give you as a warm up. So hopefully you'll get more and more used to this. Yeah. If you make mistakes from your format, yeah. So I could tell that because when I was making the quiz, I also made mistakes in it, and I had to reformat, and that was a little bit painful. Yeah. So great. This is good feedback. Options are I could scale it back. We won't be able to ask as interesting questions, or I can give you more time on the quiz if there's strong preference one way or another. Yeah, so I can set okay, so you'd like the homeworks due at midnight. I can set them due midnight on Tuesdays if you'd rather. But I don't want them due on Wednesday after class, because then people end up doing the homework during the class when they should be paying attention to lecture. So if you'd rather have the homeworks due earlier, I can do that at midnight. But this is kind of my policy. It's due before class. If you want to finish it the night before, that's probably makes a lot of sense. Oh, okay, yeah. So I'll try and figure out I'll try and give more examples of like the LaTeX commands. Maybe Peter can go and look at the quiz now and type just some of the main commands needed to format that expression inside the chat. Yeah, I'll try and bring this up during the during the lecture as things come up. I think I did a little bit about that, but I'll try and do more of that as well. It's a useful thing, just like learning how to pronounce the Greek symbols. That is challenging. So or the other symbols we'll see in class. Yeah, so that's a great idea. Yeah, so if you're doing the homework, Overleaf is great. Lots of things to search for there. If you type for LaTeX symbols in Google, but during the quiz, that's harder to do. Yeah, if you didn't format it quite perfectly, like if you didn't do the LaTeX/exp instead of exp, or you wrote e to the caret something, that's gonna be totally fine. It looked like people in the quiz 0 format stuff much better than I expected, actually. If you had written it out kind of in text, we can still read that, right? As long as it's pretty clear, right? Yeah, I did not mean for that part to be especially challenging. So don't worry about being a perfectionist on making it look like a fraction with one thing above the other. It's fine if you put a slash and parentheses around it, right? We can still read that sort of stuff pretty well. Yeah. Are the practice quizzes available? So this is the first time I've given quizzes on Canvas. I don't know. I haven't looked into giving practice quizzes on Canvas. If you look at this page, there's kind of one practice quiz to give you a sense of the scale. And I think we pretty much held up to this practice quiz. This one was also given, I think, roughly half an hour to do, and pretty much the whole class finished in 20 minutes or so, I think, when I gave this one. This is on a different topic. That's just meant to give you the scale of it. Hopefully the questions were kind of the core topics of the individual lectures we gave, right? So yeah, what's going to be asked on the quizzes are the main points in the class, right? The main things highlighted in the book, the main things highlighted in the lecture. That's what you should be doing. I might require everyone to try and make a one sheet of cheat sheet that you're going to turn in with the quiz. I find this is a great way for people to study for the quizzes. I used to allow that on the quiz, and I think people did better on the quizzes when I allowed those, because the act of creating those was a great form to study. Maybe I'll require you to turn something in. It could be blank, if you want to, but it kind of encourages you to actually do that. That's just you trying to do that yourself, and maybe then you can show that to us or the TAs and say, hey, is this a good representation of what's on here? And we can say, oh, you're missing this whole concept, which is really important. It doesn't mean it's going to be on the quiz, but it's something that is important that might be on the quiz. So that's some way I can do that. But you know, I'll try and highlight in class. I'll say this is really important. That might mean there's a good chance it'll be on the quiz. Yeah, but it's going to differ from every quiz, every topic, right? What's going to be on it. Yeah, so great. So thanks for the question. I think I answered all the questions in the chat. Those are great. I'm going to move on with the lecture, I think. There's a bunch of stuff. This lecture, there's a kind of lots of cool stuff I want to cover today. So let's try and get into it. Oh, before I do, I want to say one more thing. So we're talking about the convergence. This is the last really probability heavy focused topic. If you notice, this goes up to chapter 2.3 in the book, but we're not going to cover all 2.3. There's a bunch of examples and use cases and other stuff on sampling that comes after there. We're not going to cover. Feel free to look at that. There's some cool stuff in there. Also, we're then, oh yeah, we're not skipping chapter 4 until we get through chapter 3. Okay, great. So then we'll move on to chapter 3, which will be linear algebra. Okay, yeah, but there's more stuff in the book than we're able to cover in this chapter. So if you're interested, there's a lot more cool stuff. Great. Okay, so let me start by reminding you about these probably approximate correct formulations. This is PAC. So a sort of PAC bound is going to talk about, so we have, again, remember, we're going to have some unknown so function, this is maybe often think of it as a PDF of some form, F, and this is somehow modeling the world, the part of the world that we're interested in. And we're going to be analyzing these random variables drawn from F, okay? And we're actually getting samples from F, which are these realizations of the random variables, actual data points. That's what we'll actually be looking at. But we're going to be analyzing the random variables because that's when we can talk about the probability. Okay, and we're typically want to actually have a set x1 up to xn where these are drawn IID, that's identically and independently from this distribution. And we often want to look at some quantity, and we'll mainly now focus on just the average, the expected value, which will be 1 over n, right? Just the average of these values, okay? And then we can talk about x bar, again, is a random variable, and we can talk about its expectation, okay? And so a PAC bound, in particular, will look something like this. It will talk about the probability that our kind of accumulation of our data or our model of the data, something we pull from the data, but discussing in terms of the random variables, compared to its expected value. And if we're taking an average and these estimates are going to be unbiased, then this is the true value that we want to approximate typically, okay? So if we want to look at the difference, I put an absolute value around these. I want to consider when is the difference larger than some epsilon. And this is wrapped in a probability, so I want to say it's less than or equal to some delta. Okay, so let's again look at this. This epsilon, think of this as some error, so tolerance. I can't say it's, I want to say it's close. I don't want to say it's exactly the right value. In the continuous random variables, continuous data, I can't ever say it's exactly going to be the right value, right? The probability of anything exactly matching continuous random variables is 0, but I want to say it's close. It's close within some epsilon error of the right value, some error tolerance, and I also have this delta, Okay, and this delta upper bounds a probability. So this is a probability, and I think of it of the probability of failure, meaning that this is the probability I fall outside of this bound. Okay, so think of there's some true x bar, expected value of x bar. Expected value is something that takes a random variable and turns it into an actual value, right? So this is actual value I want to get, and then I observe something here, right? This may be the observation of x bar. I'll call this p bar, but think of this as kind of the observation, the realization of x bar. So what I actually see, and I want to know the probability that it falls within some error tolerance. All right, so I'm allowed to go in either direction within epsilon error. And then if there is some probability distribution about this, right, then there's some region out in the tail, right, that's outside of here. And so this is delta. Usually, these are often symmetric, not always symmetric. If they're symmetric, then delta over 2 on either side, probability of failure. Okay, so this is the idea of probably approximately correct. I'm never going to hit the exact expected value. I'm not going to hit exactly, so I allow some error tolerance epsilon, and it's probabilistic, so there's some probability I'm outside this error tolerance. Okay, so this is the form, but I didn't tell you about how to achieve it. We kind of talked about the central limit theorem, which says as you get more and more data, you kind of approach this, but it's kind of this nebulous, kind of more abstract thing. We know it's converging, but we can't say something necessarily very precise about it. Maybe the variance is going down if you know the variance, but that doesn't tell you what is the probability of these tails, right? How small does this actually get? Okay, and so that's what we're going to talk about today. Okay, and these are called these concentration of measure values. Okay, and so the first of these is the Markov inequality. Okay, and so we're going to talk about the 3 kind of major concentration of measure bounds. These are all going to be inequalities. They're all going to give some type of packed bound. And the difference is what we know about the problem, what we know about the random variable. That'll allow us to use stronger and stronger bounds that give us better and better estimates. Okay, and so the Markov inequality is the simplest one. Okay, we're going to have a single random variable x. Okay, and what we know about it, so we have a random variable x, and we know that x is greater or equal to 0. Okay, so we know it's greater or equal than 0. So this is what we know A, and we also know the expected value of x is known. These are the only 2 things we need to know. We need to know the expected value, and we need to know it's greater than 0. We'll see, I'll show you in a second, you can use algebra to make it greater than some other value, right? It doesn't need to be 0, but it's typically say with respect to 0. So, okay. Okay, and this is, if these 2 things are true, then we have the following rule, inequality, x greater than alpha. Okay, so x greater than alpha is less than or equal to the, and this is for any alpha greater than 0 is less than or equal to the expected value of x, which we know, divided by alpha. Okay, so this is a rule. This is if for any alpha greater than 0, for any random variable that cannot take a value less than 0, that's all we know about the probability distribution, this inequality has to hold. Okay. Okay, so this is the rule. So it looks kind of like a packed bound. It's not exactly the same. Okay, so you can do algebra inside of here. So I can do algebra, I can do linear operations on the random variables because any kind of linear operation you can factor out in various ways. So I can say set epsilon, for instance, equals to alpha minus expected value of x, okay, and delta equals to expected value of x over alpha. So this is my error tolerance and probability of failure, okay. And then what does this bound look like? Then by algebraic manipulation, I get that x minus x is greater than epsilon, and this with probability less than or equal to delta. Okay, and this delta is equal to expected value of x divided by epsilon plus expected value of x. Okay, so if you do this form, this is not the standard form, but this looks a little bit more like the pack bounds. Okay, the other two inequalities we'll look a lot closer to these pack bounds we wrote on the previous slide. Okay, but you can do algebra like this, right? I can change, instead of writing it with the value alpha, I write it with the value epsilon, which is my error tolerance. And now I get x minus epsilon. Now there's no absolute value in this case. This is a one-sided bound. That's okay. And then I can define the delta in this way. It's a little bit more complicated, but okay. So just to show you, you can do this sort of algebra, this change of variables sort of tricks. Okay, so now I want to kind of illustrate what this bound means, why it works, that this has to be true, and kind of want to do it as an analogy about what the expected value means. Okay, so I was going to try and use props in the class. Okay, here are my props. So imagine I'm some waiter that's holding a tray. Okay, and I don't trust myself to hold actual glasses. I've never actually been a waiter, so I use these stuffed animal bowling pins. And okay, so what does the expected value mean? It means that if I put my finger where my hand is, if I think of each of these stuffed animals as having a weight or as being some fraction of the total probability, then the expected value for it to balance on my hand must contain inside of its, where my fingers are, contain the expected value along here. If it doesn't, the expected value is over here, or I put my hand over on this side, it's gonna tip over. Okay, right? So that's one way to think of the expected value. If I add up all of the weight on top of here, okay, and I kind of compute the center of mass like you do in a class in physics, the expected value is exactly where this center of mass is. Okay, so this is two-dimensional, which makes it even more challenging for me, okay? But you can think about this now for one dimensions in terms of this bound. Okay, and now what the Markov inequality is saying, well, saying this is 0, and pretend that the tray itself is no weight, and saying, I know where the expected value is. Let's say it's right here. And I know I can't put this guy further left than here, right? If I keep my finger in the same spot, how far can I move one guy who's worth delta % of the mass? This guy's name is delta. How far can I move him this direction on the, assume the tray is infinite, that direction. How far can I move him and keep this same center of mass? And this is limited only by the expected value. If the expected value was further towards this guy over here, then I could move him further that way, and I pushed all the rest of the guys off to this very left side at 0. Okay, so that was a little bit of fun. Let's try and look at this kind of mathematically now. Okay. Okay. All right, so let's try and look at this a little bit more. So I'm thinking of having this tray, okay, this tray, and it could go off to infinity if I want to. It doesn't weigh anything, and I start with some sort of, like I just know that the expected value of some random variable drawn from underlying distribution is right here. Okay, and it could be that the distribution looks like this, but I don't know what the distribution. All I know about it is that the tray starts at 0. There's nothing further to the left than this point 0, and the expected value is right at the spot. And so I want to say, like, how far can I push some delta probability to, like, off to the right, so that how much probability and how far can I push it off to the right, so that it still is the same expected value. So what I can think of doing is have a different, I want to have the same expected value for a different random variable from x prime, where I have a lot of the mass right here. And I'm going to have some little thing out here. This is delta fraction of the mass. Okay. How far can I push this off to the right? Okay, so this is basically what the Markov inequality is telling us. Let's see mathematically what's going on. Okay, so I have expected value of x. Okay, and if I've done this green distribution here, I know that the expected value is the probability that it's going to be at one of these two different locations. Let's call this location alpha, where I've put all of this mass. So the probably it's greater than alpha, but I don't want to waste it by pushing it further than this bound, right? So let's say alpha is out here. So that means that yeah, so that it's either going to take a value of 0 or a okay, in which case I multiply it by the probability that x is equal to 0. This is the green distribution, the most extreme case, plus it takes on a value of alpha, and this is times the probability that x equals alpha. Okay, and so if I set, so let's say I want to solve this for a pack bound. So or for the definition of Markov inequality. So I say the probability it's here is going to be delta. Okay, so I'm allowed delta probability that I'm going to be very far away. Okay, and I know that then this has to be 1 minus delta. Okay, so then I'm going to get that this is going to be 0 times 1 minus delta plus alpha times delta. Okay, and this is 0 times something, so it goes away. So this is alpha times delta. Okay, and then I want to solve for the value of delta that I can take to put it alpha far away, and that's exactly going to be that expected value of x divided by alpha is going to be delta, right? Just by dividing through by alpha. Okay, so if I put something alpha far away, some mass, how big of a probability can I put out there? That's delta probability. This is where the inequality comes from. Okay, and I can put it closer, that's okay, but I can't put it further away. All right, so this is kind of how effectively how you prove that this Markov inequality. So let's go through a couple of other examples of this, and so I'm not going to ask you to prove it on the homework or quizzes. I just want to give you an intuition of what's going on. What I expect you to be able to do is to be able to use these inequalities. Okay, so I'm going to show you 2 examples now. Okay, this is one example with this blue distribution, and I want to say that this extreme probability, this alpha is going to be 5 in this case. And I want to, and the way I've colored this in this example here, this delta, let's say it's 1/10 in this case. Okay, and so it's going to have an expected value of x equals about, this is about 3.2, something like that. Okay, now I want to show you a different example here. In this example, again, I'm going to have delta equals 1/10. Okay, so, and again, I have alpha equals to 5. But now the expected value, the expected value here is about 0.5. Okay, so this example is kind of the extreme case. If I have this case, the Markov inequality is going to give me a pretty good estimate of how much mass can be alpha away. If I were to apply the Markov inequality in this case here, I'm going to find that the prediction just using alpha. So if I apply the Markov inequality, right, I just look at these quantities. I just look at alpha and epsilon, and I will write down that the probability that x is going to be greater than alpha equals 5, right? This should be less than some quantity. And if I calculate 0.5 divided by, and this is slightly more than 0.5, let's say 5. Yeah, this is supposed to be about 0.65, it turns out. Okay, if I calculate this by 5, I'm going to get 0.12. Okay, so this is pretty close. My bound is, I say, no more than 12% of the mass is greater than alpha, and the true case is 10%. So this is a pretty good bound. It's an upper bound on the quantity. If I do it with this example instead, I'm going to get that the probability that x is less than 5 is less than or equal to about 3.2 over 5. And this is going to be about 0.6. So I'd say there could be 60%. With this expected value, I might get 60% of the probability to be 60% of the probability to be greater than 5 if all I know is this expected value, which is not a very good estimate. It's only 10%, right? So this is not the extreme case. So I don't know what the real distribution is, but I can only get an upper bound here. Okay, so in this case, it's not a great bound. In this case, it is a good bound. These are kind of two different categories I might think about. Okay, it could be even worse than, it could be, if it didn't have this mode out here, maybe it's even a worse estimate. Okay, so this is just kind of some intuition so far. Let me give you an example of how we'd actually a problem where we would actually use this. Okay, so let's say that in June, the expected kind of rain at the Salt Lake City airport, right? So it's going to be some random variable r. Okay, and so I can look at the expected value of r. If you look this up, it's roughly 20 millimeters of rain. It's a pretty small amount, right? 20 mil. If you're not used to the metric system, it's pretty small. Maybe someone can look up how many inches that is. That's a small number of inches. Okay, so let's say I'd like to know what's the probability that the rain in June in SLC is greater or equal than 50 millimeters. So more than 2.5 times the expected value. What's the probability that we have this? Yeah, so it's a great question. Let me finish this example first. So, okay, and I can write this down as a probability that rain is greater than 50 millimeters. And this is less than the expected value of R divided by 50 millimeters. And this is 20 over 50, and this is 0.4. So there's a 40% chance, if I only know the expected value, the rainfall has to be positive, right? If I only know the expected value, there's a 40% chance we're going to get a big rainstorm. And in June, we're going to have more than 50 millimeters of rain. Okay, so that's an example of how you would use this. And we'll see another bound, and we'll reanalyze the same problem with a little bit more information, and we'll see that we can get a much better bound if we have more information. So okay, so there's a question, wondering if there's a stronger constraint on alpha, like what happens if alpha is less than expected value? It appears you get an upper bound that's greater than 1. Yeah, okay, so let's look back at the formulation here, right? So far, this just gives me an upper bound on the probability. At this point, like the example I just did, less than 40%, the probability is at most 40%, it's going to exceed this. This inequality is not always useful. Sometimes, you're right, if I set alpha less than the expected value, say, what's the probability that is greater than 10 millimeters, right? So let's say I redid this. Well, how about the probability that R is greater than 10 millimeters? Okay, all I know the expected value, and it's greater than 0. If I plug this in, I'm going to get the expected value 20 millimeters over 10 millimeters, which is equal to 2. But I know a probability can be at most 1. Well, this makes sense, right? It could be, I could think of these two different distributions again. One is the expected value is 20 millimeters. Here's 0. And I can have two distributions here. Okay, and one of these might be like this. So the distribution is very concentrated. And so if I write 10 millimeters, it's always greater than 10 millimeters. So it is probability 1, right? So it could be it's very concentrated. So I just knowing the expected value, I can't say anymore. On the other hand, it could be that sometimes it's 0, and sometimes it's going to be 60 millimeters, a third of the time. That might be more like what it looks like. This June, I don't know, some Junes we probably get almost 0 rain, and other Junes we'll have a couple of storms and we'll get a whole bunch of rain. In that case, then the Markov inequality gives a pretty reasonable estimate of what's going on. What would be a sentence in words for the answer we got for rainfall in the Markov inequality? Yeah, so the sentence in words is the probability that the rain in June in some upcoming June for Salt Lake City is greater than 50 millimeters. That probability is at most 0.4. So it's at most 40% of the upcoming Junes. We would have more than 50. We would not have more than 40% of the upcoming Junes to have 50 millimeters of rain. Right? Kind of said that a couple ways without a little bit of a weird sense there, but hopefully that helps. Yeah. By only knowing the expected value, that the probably, oh yeah, great, good, yeah, great. In the chat, someone said even more eloquently than I did. Right. So okay, so that's one example. And again, this is just one inequality. We're going to get different inequalities, and to get a bound, you might want to try all of them that you can use and see which one gives you the best bound. They just give you an upper bound on this quantity. So the next one is going to say it's less than 1% of the time. with kind of consistent information, slightly different information, but consistent. Okay, so we'll see this. Let me state now the Chebyshev, that's a B, Chebyshev inequality. Okay, and so this now has a random variable x. Okay, and now I know two things about it. I know the expected value of x, and B, I know the variance of x. Okay, so I no longer, it can take values less than 0. That's okay. And so, but I know the expected value. I also know the variance. I also have a bound on the variance. Okay, and then this allows me to state for any parameter epsilon greater than 0, I can say that the probability that x minus the expected value of x, right? So that my random variable is different from the value I want to get, is greater than epsilon. This is our pack bound, is less than or equal to the variance of x divided by epsilon squared. Okay, so this looks similar to the Markov inequality. I'm getting some probability on the left, and on the right, I'm getting some, now the variance is in the numerator, which is a squared quantity, it's squared units. So I get to divide by this error sort of term squared. That means as my kind of tolerance increases, my bound on the probability goes down so quadratically instead of linearly. So this is kind of, I'm able to get better bounds on the probability this way if I have good bounds on the variance. Okay, so for in the pack bound, right, in order to get the pack bound, I just said delta equals to the variance of x over epsilon squared, right? So then it's exactly these pack bounds that I was talking about. Okay, and now this difference, because is two-sided, I've got the absolute values here. So I've got absolute value in x or y. It means that I could be, I can't be too far from the expected value in either direction. Now, typically within this course and in the problems I ask you to do, I'll only look at one direction. And it turns out there are stronger bounds versions of this that only bound in one direction, and the probability is roughly half. It's not, these things are not always symmetric. And so we'll just state the two-side versions, but if you only need to use one side, you only need to use that one side. We'll see examples of this. Okay. Okay, good. So let's go back to this. So this is this Markov, or sorry, the Chebyshev inequality. Okay, so this is the second of the three inequalities we'll be talking about today. And this one uses the variance in addition to the expectation. Okay, so let's go back to our example with the rainfall. Okay. Rainfall in June in SLC, and this is some random variable R. So let's say again, recall that the rainfall is going to be the expected value, expected rainfall is 20 millimeters. And let's say that we now also know the variance of the rainfall. And let's say we're given that this is equal to 9 millimeters squared. Remember, variance is a squared quantity. So to make the standard deviation is the square root of the variance. The standard deviation would be 3 millimeters. This would be a pretty tight concentration around 20. That means, you know, roughly 2/3 of the time, the value is between 17 and 23, right? That's one standard deviation away. This is a kind of rule of thumb. So this is probably not what it's like in Salt Lake City, but let's assume we have this knowledge. For instance, if this was like in Florida and June, maybe you get like 20 inches of rain. I don't know what the rainfall is in Florida, maybe. So yeah, so it's then think about that would be a much tighter concentration. Sure. Okay, so let's go back now and ask our question. Let's bound the probability that the rainfall is greater or equal to 50 millimeters with this information. Okay. And so the first step we can do, we're going to do some algebra to do an inequality here. We're going to add, or we're going to subtract 20 millimeters from both sides, basically. And then we're going to start by saying the probability. And so first this will be an equality. The probability that the rainfall minus 20 millimeters, which is the same as the expected value of R, is greater than 30 millimeters, right? So this is this is inequality, right? I can just add or subtract 20 millimeters from both sides of this equation, right? I haven't changed anything, but I'm going to make it so how about I just do it in 2 steps now? So then I can make this an inequality by saying that the rain minus the expected value of the rain (30 millimeters). But let's say that the absolute value of this. Okay, so maybe the rain was 10. Yeah, I guess in this case, the rain can never be far enough negative for this to actually matter. But the absolute value captures cases where, say, the rain was 10 millimeters is what we actually saw, and the expected value was 20. So this was a negative number, but now I have the absolute value. Okay, so this means this probability could be bigger. It could be even larger in this case. And the reason I did this is because this is the form of the Chebyshev inequality. This is the left-hand side of the Chebyshev inequality now, which means now I can apply the Chebyshev inequality to say this quantity, right, now is less than the variance of R divided by 30 squared. Okay, and I know that the variance is 9 divided by 30 squared is 900. This is 0.01. So now, using the using the Chebyshev inequality, the probability that there's and knowing this extra information here, that the variance is pretty small, now I can say that the probability that I see a rainfall next June in Salt Lake City Airport of more than 50 millimeters happens less than 1% of the time. Right? So if I have a good bound on the variance, then I can get a much smaller probability of some sort of event. This information is consistent with the previous example. I've added more information. It allowed me to apply this stronger bound and get a better upper bound on the case here. Okay. Now, it could be that the variance is actually very high, right? If the variance instead was like, there's some limit to how high it can be because it has to be greater than 0 and the expected value is bounded, right? But let's say if the variance is really high, is like is so going to be like is going to be 90 millimeters squared instead, right? Then I'm going to get 10% bound, right? So if instead this was 90 millimeters squared, then I would get 90 over 900, and this would give me 0.1, give me 10%, which is still better than I get with the Markov inequality. If it was 900 millimeters squared, then it would not be very helpful. I would get a value of 1 here. right? So if you don't have a good bound on the variance, then it's not going to help you. But if you do have a good bound on the variance, then you can get a kind of a better bound on these extreme, these tails of these probability distributions. Could you go back one screen? Okay, yeah. Yeah, okay, so let's speak through this inequality again. And most packed bounds look like this, although sometimes they change the two inequalities. It says the probability that the difference, right? I know this is really confusing the first time you see it, but this is kind of the language of these things, so it's good to spend some time on it. So let's say this is our actual error, right? This is our actual error. And so the probability that the error is bigger than the tolerance, right? The probability the error is bigger than the error tolerance, epsilon. I want that probability to be small. So I want to upper bound the probability that is big. I want to upper bound the probability of the tail. Okay, so if I have some sort of data and I have some unknown distribution here, it might look like this. It might look like this. I'm not sure what the distribution looks like. I might know something about the expected value of X, and I might know something about the variance or the standard deviation of X, or I might just know that it's greater than 0. And I want to pick out some sort of, so then what I want to do is pick some error tolerance, epsilon, right? I want to say the probability that I'm outside of here, the probability of failure is outside of this error bound, right? That my error is bigger than this epsilon allowable. That's going to be the probability, the area under this curve here that's outside of this blue safe region. So in this example, well, almost the error tolerance is actually going to be only the error tolerance is actually going to only be 30 millimeters because I'm measuring the distance from 0. This distance is 50 millimeters, and the expected value is 20 millimeters, right? So I'm just measuring the distance from 0. That's a more natural way to put it. And so that's why I did this change, this kind of the first step here. The first step I did here is I said, I want to know the probability it's greater than 50, but I need to subtract 20 so I can turn it into an error formulation, right? So that's why I did this first step. So now I've got a 30 after I've done this formulation. Now this error is 30 here instead of 50, because that's the difference from the expected value. Great. So hopefully this is starting to make sense. You will, I think really the best way to do this is to do some examples, and there are some examples on the homework that we'll ask you to do. We'll ask you to compute both of these bounds, see which one is more useful, and I think we've set the parameter. So sometimes the Markov inequality is more useful, sometimes the Chebyshev inequality is more useful. Okay. Okay, so I want to do one more important observation about the Chebyshev inequality I could not do with the Markov inequality. Okay, this gets back to our concentration of measure and the central limit theorem here. Now let's say I have random variables x1, x2, up to xn. Okay, I tell you which is more useful. The Markov inequality you can apply more generally, but the Chebyshev inequality gives usually better bounds. But it depends. Sometimes the Markov inequality gives, you have to try them both and see which is more useful. I think we'll do examples either in this class or in the data mining class that use both of them, where sometimes the best thing you can do is the Markov, sometimes the best thing you can do is going to be the Chebyshev. Usually, and then we'll do the Chernoff-Hoeffding bound next. And that one, usually start with that. If you can use that, do that. That usually gives the best bound, if not Chebyshev, if not Markov. But, you know, it depends what information you have. So how will you know which one is better? You'll probably try them both and see which one gives you a better bound. They're both correct. They both give you upper bounds, right? So if I look at a distribution here, I've got some statistics, I've got some expected value, and maybe one of them, they give upper bounds. So it says that I want to know the probability of exceeding some sort of event. Let's say I want the probability to be less than 10%. How far can I push alpha? Maybe this is from the Markov, gives me this upper bound, and maybe the Chebyshev gives me this one, which is worse. It's a larger upper bound, right? But both of them can be correct. They're both upper bounds on some value, right? They're both of them are going to be inequalities. So you calculate both of them and you take whichever one gives you a stronger inequality. So, okay, so good. So let's go back to something nice happens when we have now multiple random variables. And again, we have x bar, which is the random variable, which is 1 over n, which is the average of these. Okay, now we're going to be able to look at the average of multiple of these and get an even better, an even stronger bound. Okay, and so this works because we know, based on some inequalities we talked about, that the variance of x is going to be equal to the variance of any of these xi's. Let's remember these are iid from some unknown distribution, okay, divided by n. Okay, we know this from the central limit theorem. You can also see this by just working out the definition of the linearity of expectation and how scalars factor out by taking their square when you they factor out the variance in this way. So the variance decreases by a factor n as we have averaged more of these things together. Okay, so what this means is if we can plug this directly into the Chebyshev inequality, and so now let's say I want to estimate the difference now of x bar from the expected value of xi, right? So I want to know the expected value from this unknown distribution f. If I use one random variable that I've drawn from it, I do what I did before. But now I can use the random variable x bar, which is the average of a bunch of these things. Okay, so the probability this is outside my error tolerance is now the variance of x bar divided by epsilon squared, which is equal to, or let's just write the less than or equal to, the variance of xi divided by n times epsilon squared. Okay, good. So what this is saying is, as I average more of these random variables together, my bound on the probability going beyond the tail goes down by a factor of n. So I can now quantify how quickly I'm shrinking the probability of my tail. It's going down by a factor of n using this Chebyshev inequality. I can't use this trick with the Markov inequality because I only use the expected value, and we know by the central limit theorem when I average things, the expected value stays the same, right? And if it stays above 0, well, the average stays above 0. So I don't get any wins there. But now because I'm using the variance, I know the variance shrinks linearly, which means that the probability of the tail shrinks linearly as well. Okay, so now I can do and say, so I can do, for example, I want to say, So given error tolerance epsilon and the probability of failure delta, okay? So how big, how many samples, the quantity n, are so needed, okay? And you can solve for this now, just some algebra, and you need that it's sufficient for n equals to the variance of xi divided by, this is just by setting this equal to delta, the variance of xi divided by epsilon squared delta. Okay, so as the probability of failure decreases, the number of samples you need are going to increase linearly. So if I figure this out for 10% probability of failure, and how many more samples do I need to get to 1% probability of failure? I need a factor 10 more samples. Okay, so it goes down with the number of samples in some linear way, and it's great, right? This is good. The Chernoff-Hoeffding inequality will have this number of samples I need to get a small probability of failure to go down exponentially faster. Okay, so is this clear what happened here? Let's say I'm given the variance of xi. If I'm given these three things, these three quantities, and the homework, we may ask you to solve some basically inequalities like this. So I'm given these three quantities, the error tolerance, the probability of failure, and the variance of some random variable. And the error tolerance captures distance from the expected value. That's kind of built into it, right? Then I want to say, how many samples do I need to get this high accuracy? Right, and I can just take this equation here. I just take this equation and I can solve for the value n. I multiply both sides by n, I divide both sides by delta, and this is the solution I get. Okay, so if I had more than that many samples, I guarantee that with probability at most delta, with probability at least 1 minus delta, I have no more than epsilon error. Or there are other ways you can change these inequalities around to say that. Okay, so this is a very powerful thing about the Chernoff-Hoeffding bounds. It tells you some very, this is the Chebyshev inequality. It tells you a very specific way that the central limit theorem works. If you have this information, I can start to quantify these effects in ways, and this will allow me to get bounds on how many iterations do I need to run an algorithm, or how many samples I need to draw in a randomized algorithm to say it's so accurate. How many samples do I need to draw from the real world to get this accurate this pack bound for this quantity I'm trying to estimate, right? So this is a very important thing to do. So okay, so let's great. So let's last 17 minutes tell you about the Chernoff-Hoeffding inequality. Okay, and so this has been kind of reinvented in various forms by Chernoff, by Hoeffding. So like there's some version attributed to Azuma. Apparently, I think if you look up the standard form of this, I think it looks more complicated than what I'm going to present. The form I'm going to present, I find, is by far the most useful. A statistician would do some algebraic manipulation and write it in a completely different way that I think is less intuitive to me. And this is typically, but in machine learning and data mining, this is kind of probably the most useful form I'm going to describe. Okay, so now this is explicitly stated by, I'm going to have n random variables, x1, x2 up to xn. And these are going to be IID from some unknown distribution f. Okay. What do I know about these? I know the expected value of each xi, and they're all the same because they're IID. And I also know that each xi is going to be in some range, bottom to top, like between 0 and 10, between 2 and 8. And all I really care about is this quantity delta, which is t minus b. Okay, the difference between the two extreme values. How large can this be? Okay, so I don't know the variance anymore. I don't use the variance. I use that the random variable falls within a certain range of a certain width. And this is my scale quantity. Okay, scale quantity for Markov is the difference from the expected value and 0. For Chernoff-Hoeffding, for the Chebyshev inequality, it's the variance, or the standard deviation gives me the scale bound. Now I say there's an absolute upper bound on the range. I know that the range cannot be more than 100 millimeters, right? That would be, then delta would be 100 in this case. Okay, so now the Chernoff-Hoeffding inequality is written as follows. It's explicitly, this inequality is now going to explicitly be about x bar. Okay, this is 1 over n xi. Right, it's explicitly going to be about this average. That's going to explicitly be about how well this stuff concentrates. Okay, so then I can say the probability that x bar minus the expected value of xi, right, or x bar, these are the same, right, is greater or equal than some error tolerance epsilon, is going to be less than or equal to 2 times exp, that's e to the power, right, e to the power something. So look kind of like a form of a Gaussian a little bit, right? So that means it's exponentially decaying. 2 epsilon squared n divided by delta squared. Okay, so this looks a little bit more complicated, but you know, this this quantity again is my delta probability of failure. And what's happening as n, I'm doing an e to the negative power. So think of 1 over e, right? So this is kind of 1 over e to this power. So that means as n gets larger, this is going to decrease exponentially. Right? So that's great, right? And as epsilon gets larger, yeah, as my error tolerance gets larger, yeah, yeah, so then that's going to grow. Yeah, then we'll go and it's illustrated to solve for n here. Yeah. Okay. So what are t and b here? So let's say an example for t and b. Would be, say that the rainfall is going to be in the range 10 millimeters to 60 millimeters, right? So then this is the bottom, b is the bottom, and t is the top. So t is 60, b is 10, and delta, then this would be, delta would be 60 minus 10 equals 50. Okay, so that'd be an example. If I know rainfall has to be between 10 and 60, maybe I said, okay, I don't know for sure, but historically it's never been less than 10. It's never been more than 60. So I'm just gonna assume that, right? There could be some sort of physical constraint here. Often these random variables might, a common case is random variables are like some flips of a coin. So they're actually binary and they're either 0 or 1. And so then delta actually becomes 1 because the bottom is 0, the top is 1. It can't actually take a value in between, but that's okay. right? That's a pretty common example, and that's a physical constraint that they're actually between 0 and 1. But you know, there are a variety of situations where you get constraint that allows you to get this very strong bound. Yeah. So okay. So let me say one thing so we can compare it to the Chernoff to the Chebyshev inequality here, right? So on the pack bound, we get that by solving for this term delta, right? This is equal to 2 exponential e to the power 2 epsilon squared n divided by delta squared. Okay, so let's now solve for n in this case. Well, what happens? How big does n need to be? If I'm given epsilon and delta, right? I'm given a pack bound epsilon and delta, and also this uppercase delta, this absolute range of the random variables. Then how big does how many samples do I need in order to get a good bound, right? So given epsilon, delta, and delta, how many samples n are so needed? Okay, and we have to solve for n now. So we basically take the natural log of both sides, and then what you end up getting is n is going to be delta squared over 2 epsilon squared times the natural log of 2 over lowercase delta. Okay, so if you look at this form and compare it to the Chebyshev inequality, this term, the 1 over epsilon squared, is basically the same. And so that's basically to get an error tolerance epsilon for a quantity based on some scale. It's these sort of things. So the number of samples you need kind of as epsilon decreases, number of samples increase quadratically. And this is central to the central limit theorem. To get the kind of the standard deviation of your concentration to go down, you need 1 over square root n, kind of, it scales with 1 over square root n. So this is kind of a fundamental property. But if I compare to this term delta, the probability of failure, now with the Chernoff-Hoeffding bound, this goes down exponentially quickly. If I want to get, basically, if I want to get twice the probability of failure, or a factor e more, or I want the probability of failure to go down by a factor of e, or say a factor of 2 roughly, I need to roughly double the number of samples. Or no, sorry, I have to get roughly 1 more sample. It used to be to go down by a factor of 10, I need to get roughly 10 times more samples. Now to go down by a factor of 10, I need to get 1 or 2 more samples, right? So every factor 2 it goes down, or every factor e it goes down, I need to get 1 more observation. This means the error of the tail bound goes down exponentially faster than with the Chebyshev inequality. Should be natural log of delta over 2 instead of natural log of 2 over delta. So let me just do this in a bit more detail. This is I've made that mistake when doing this a bunch of times. Very natural. So what I'm going to do, I'm going to write 2 over delta is equal to x of negative 2 over epsilon squared n over delta squared. And I can take the natural log of both sides. Natural log, oh, actually first, this is e to the negative. So I want to do, so that means that's basically I'm taking to the power -1. So I can get rid of the negative by doing, right, what did this should be, I did this is delta over 2. Okay, so to get rid of the negative sign here, I do 2 over delta now without the minus sign. Okay, now I take the natural log. And then I can solve for n. Right? It's easier if it's on the, yeah, so n equals big delta over 2 epsilon squared natural log of 2 small delta. Right? Okay, so the key step here is the negative. When I take away that negative sign, I'm flipping this, and that's what happens. Great. Yeah, so that's pretty easy to miss. So it's a good question. So okay, so I'm going to try and do one example here, and we'll try and compare Chernoff-Hoeffding bound and the Chebyshev bound. Okay, and I might go a little bit over time, but we'll keep rolling a little bit. Okay, so I'm going to roll some dice, some fair dice, n equals 120 times. Okay, and I want the random variable t going to be the number of times I roll 3. Okay, it's a fair dice, so the expected number, right? The expected value of t is equal to 120 times 1/6, which is 20. Okay, the expected number of 3s I roll is going to be 20. I want to bound the probability that t is going to be greater than 40. Okay, the probability I roll more than 43. So let's say greater or equal than 43s. Okay, so it's you can explicitly calculate this probability. We aren't going to do that. We're going to use the Chernoff-Hoeffding bound and the Chebyshev inequality to get upper bounds on this probability, and we'll see how they work. Okay, so the first thing I'm going to do is I'm going to so I'm going to say that each, so that I'm going to decry random variables xi, which is going to be equal to 1 if a 3, or a 0 if 1, 2, 4, 5, 6. Okay, and so then in this case we'll have that x bar is going to be 1 over n of these xi, and t is going to be x bar times, and so n in this case is 120, is going to be 120. Okay, so this is some just linear rewriting of the variables here. Okay, so now if I want to bound this probability that t is greater than 40, I can first say the probability that x bar is greater than 1/3. So this is n. Yeah, so I want to do this, but it's equal to probably x bar is greater than 1/3, and this is less than or equal to the probability that x bar minus the expected value of x bar, right, which is 1/6, right? So is that the absolute value of that is greater than 1/6. Okay, it's greater or equal than because I added these. This greater or equal than is because I added these absolute values. Okay, but now this looks like the left-hand side of the Chebyshev inequality with n random variables and the Chernoff-Hoeffding inequality. Okay, good. So now if I apply the Chernoff-Hoeffding inequality, okay, I'm going to get that this is less than or equal to 2 exponential minus 2 times the, let's see, this is 1/6 squared, right? This is my epsilon times n, 120. And delta is 1, so 1 squared, right? So let's see, this is equal to delta squared. This is equal to epsilon squared. This is equal to n. Okay, and so I can solve and simplify this. This is equal to 2 exponential of, if I cancel, it's like 1/36 times 120 times 2, it ends up being minus 20 divided by 3. Okay, and this is less than or equal to 0.0026. Okay, so less than 0.3 of 1% of the time, I get more than, so less than 3 out of 1,000 times, less than 26 out of 1,000 times, or out of 10,000 times, I am going to roll more than 43s. It's pretty unlikely. Okay, great. So I've really driven this probability of failure down pretty small. Okay, so why is uppercase delta 1? Yeah, uppercase delta is 1 because if you remember, my this uppercase delta is 1 because my random variables are xi, right, over here, and my top is 1 and my bottom is 0, right? So the random variable only takes values between 0 and 1, right? This is a pretty common case. Either it happens or it doesn't happen. It's more general. This is a quite general form I presented, but a common case is like this binary event. Great. So I've finished the inequality example inequality with the Chernoff-Hoeffding bound. Oh, okay. So why is epsilon equal to 1/6? Well, because 1/6 is right here, right? This is epsilon, right? Remember that this is the form, right? This is the form of the Chernoff-Hoeffding inequality, and this guy right here is my epsilon, right? So if I get this left-hand form on the right side, then that's where epsilon comes from. And that's 1/6 is because it was 1/3 was equal to 40%. That's more than 1/3 of the time. And I subtracted the expected value, which was 1/6 of the time. So 1/3 minus 1/6 is 1/6. And that's where this comes from. This is equal to 1/3 minus the expected value, which is equal to 1/3 minus 1/6. Right. So I've run out of time. So I'm just gonna keep going as long as I'm here. You can stop and ask questions or whatever, but I'm gonna just and this will be on YouTube. I'm gonna go and do the plug in the Chebyshev inequality. So to do the Chebyshev inequality, I know that the variance of each xi, it turns out for this distribution is 5 out of 36. So if I have a binomial, a Bernoulli distribution with 1/6 probability, end up getting 5 sixes is going to be the variance. And so then the right, so if I plug in the variance of so that means the variance of x bar is going to be 120 times 5 of 36, and this is going to be sorry, 120 divided, sorry, 536 divided by 120, right? The variance goes down. And let's see, the example in my book, I'm doing slightly different change of variables here, but we'll plug this quantity in. Okay, so now this is going to be less or equal to this variance of x bar divided by, in this case, 1/6 squared. And this is going to be 5 of 36 divided by 120 divided by 1/36. Okay, good. I'm getting some cancellation here. And so this will be equal to 5 out of 120, which, if I did this correctly, I think is about 0.042. Okay, so if I did this correctly, it's about 4% of the time. I say, using the Chebyshev inequality, I can only say it's how unlikely is it to get 43s on 120 rolls? Well, it happens less than 4% of the time, or less than 4.2% of the time. Okay, so I have two bounds here now, right? I have this less than, 2 or 3 out of 1,000, or less than 42 out of 1,000, right? So both of them are correct bounds for the true probability, but the Chernoff-Hoeffding one is better. Okay, and if I have more rolls, the Chernoff-Hoeffding one's going to be even better. If I have less rolls, they're going to be more similar to each other. Yeah. So okay, great. So this is what I want to cover in the lecture today. Went a few minutes over. There's a lot more in the book if you want to know more about how to apply this, some more complex examples. We'll discuss these later in the semester, but we won't actually work through a lot of them in details. But I want you to practice working through them so you kind of understand how to think about these sort of things, because we'll be taking lots of data, taking things that look like averages or basically are averages, and that's going to be our model. And we want to understand how, as you get more data, you get a better and better estimate, and why the bounds look like they have these packed bounds that look like epsilon and delta. And you typically use these 3 bounds: Markov, Chebyshev, or the Chernoff-Hoeffding inequality. So great. So thanks.